On June 23, 2025, a telescope in the mountains of Chile turned on for the first time. In just over 10 hours of test observations, it found 2,104 asteroids that had never been seen before by anyone, ever, in the entire history of astronomy. 7 of them passed close to Earth's orbit. All were discovered before the telescope had even officially started its real mission. That's not a typo, and it's not a fluke. It's the Vera Rubin Observatory doing, in half a day of testing, what took previous generations of telescopes years to accomplish. Rubin isn't like other telescopes. It doesn't focus on one target at a time. It's built to photograph the entire visible sky over and over every few nights for the next 10 years, creating what astronomers are calling the largest movie of the universe ever made. In its first 10 hours, it already found something moving through our solar system faster than anything we'd ever recorded. This is the story of a telescope built to find nearly everything that moves, explodes, or changes in the night sky, and what it's already found in the first few months of being switched on. This is Deep Space Declassified. New classified file every week. Subscribe before we go further. Let's get into it. The Vera Rubin Observatory sits at the summit of Cerro Pachón in Chile, a location chosen specifically for its dry air and exceptionally dark, stable skies. Some of the best observing conditions anywhere on Earth. It's the result of more than 2 decades of planning, engineering, and construction, jointly funded by the U.S. National Science Foundation and the Department of Energy's Office of Science, at a total cost of roughly $810 million. The observatory is named for Vera Rubin, the astronomer whose work in the 1970s provided some of the first strong observational evidence for dark matter, measuring how stars orbit within galaxies, and finding speeds that only made sense if each galaxy contained far more invisible mass than anyone had assumed. It's a fitting namesake for a telescope explicitly designed, in part, to search for further clues about dark matter and dark energy across the largest scales the observable universe offers. At the heart of the observatory is an 8.4-meter telescope paired with the largest digital camera ever built for astronomy. A camera roughly the size of a small car, capable of capturing an area of sky many times larger than the full moon in a single exposure, at a resolution sharp enough to pick out extremely faint, fast-moving objects that previous telescopes would have simply missed. On June 23, 2025, Rubin's team revealed its first images to the public in an event held in Washington, D.C. A moment astronomers had been anticipating for the better part of a decade. What they showed the world wasn't just pretty pictures. It was proof of concept for an entirely new way of surveying the sky. Using just over 10 hours of test observations, the team had already captured millions of galaxies and Milky Way stars, along with those 2,104 previously undiscovered asteroids, including 7 whose orbits bring them relatively close to Earth's own, though none pose any danger. One video assembled from over 1,100 individual images showed a detailed close-up view zooming out to reveal roughly 10 million galaxies within the camera's wide field of view alone, representing, astronomers noted, only about 0.05% of the roughly 20 billion galaxies Rubin expects to observe over its full 10-year mission. For comparison, ground and space-based telescopes combined currently catalog roughly 20,000 near-Earth asteroids after decades of dedicated search effort. Rubin's science team projects that within its first few months of full operation, it will find over 1 million new asteroids across the solar system, more than doubling humanity's entire current tally, essentially overnight by astronomical standards. Rubin's core scientific mission is called the Legacy Survey of Space and Time, or LSST, a 10-year project in which the observatory will photograph the entire visible southern sky roughly every 3 to 4 nights, continuously for a full decade. The strategy is fundamentally different from how most telescopes operate. Rather than pointing at one specific target and studying it in depth, Rubin systematically rephotographs the same patches of sky over and over, building up what is effectively an ultra-high-definition time-lapse record of the entire visible universe. Every time it revisits a patch of sky, its processing system automatically compares the new image against everything captured before, flagging anything that has changed, moved, brightened, dimmed, appeared, or disappeared. Over the full 10-year survey, Rubin's science team projects it will detect roughly 89,000 near-Earth asteroids, 3.7 million asteroids within the main asteroid belt between Mars and Jupiter, and 32,000 icy objects in the distant, frozen reaches beyond Neptune. That's not a modest improvement over previous surveys. It's a scale of discovery that fundamentally changes what's possible in solar system science, turning asteroid and comet discovery from a specialized, painstaking pursuit into something closer to a byproduct of routine, automated observation. Rubin's speed and sensitivity have already produced results even its own science team didn't fully anticipate this early. In data collected across just 9 nights during its commissioning phase between late April and early May 2025, astronomers discovered an asteroid rotating faster than any object of its size ever recorded. The asteroid, designated 2025 MN45, is a main belt object over half a kilometer in diameter, roughly 5 football fields long, and it completes a full rotation once every 1.9 minutes. For an object of that size, that's an almost violently fast spin. Asteroids rotating that quickly at that size push right up against the theoretical limit at which centrifugal force would start tearing a loosely bound rubble pile asteroid apart. It wasn't alone. The same brief observation window turned up 18 additional super and ultra-fast rotating asteroids, including 2025 MJ71, spinning once every 3.7 minutes, and several others completing full rotations in well under 20 minutes. Nearly all of the newly identified fast rotators live in or near the main asteroid belt, at distances where such rapid spins hadn't previously been well documented, a direct result of Rubin's unprecedented combination of light-gathering power and precise, repeated measurement over a short observing window. The significance of finding 19 ultra-fast rotators in 9 nights of preliminary pre-mission commissioning data is easy to understate. Discoveries like this, historically, have required years of dedicated observing campaigns, specifically designed to catch asteroids at exactly the right rotational phase to measure their spin rate accurately. Rubin's design makes this kind of discovery almost incidental, because the observatory photographs the same regions of sky repeatedly with precise, closely spaced timing between exposures. It naturally captures the brightness variations caused by an asteroid's rotation as a side effect of its normal survey operation. Data that would otherwise require a dedicated, specialized observing campaign to obtain. That has real scientific value beyond the raw discovery count. An asteroid's rotation rate provides crucial information about its internal structure and composition, whether it's a solid, coherent chunk of rock or a loosely bound rubble pile held together mainly by weak mutual gravity. Understanding that distinction matters directly for planetary defense. How you would deflect an asteroid on a collision course with Earth depends heavily on whether you're dealing with a solid object or a loose gravitational aggregate that might respond to an impact in a very different way. Beyond individual objects, Rubin's most transformative capability may be temporal. Its capacity to detect anything in the sky that changes, on almost any timescale, across the entire visible sky simultaneously. Supernova, the explosive decks of massive stars, currently get discovered by a patchwork of surveys and observatories, often days or weeks after the explosion has already begun, once someone happens to notice the new point of light. Rubin's systematic every few nights coverage of the entire sky means it's expected to catch far more supernovae far earlier in their evolution, potentially catching some explosions within hours of their onset, rather than days, giving astronomers an unprecedented head start on studying exactly how these events unfold. The same repeated wide-field coverage extends to variable stars, gravitational lensing events, and, directly relevant to earlier episodes of this series, a dramatically improved chance of catching interstellar objects like Oumuamua and 2I Borisov much earlier in their passage through the solar system, rather than discovering them, as happened with both previous interstellar visitors, only after they were already departing. Rubin's science team explicitly expects the observatory to detect multiple interstellar objects per year once its full survey is underway, compared to the mere handful found across the entire history of astronomy before it. Rubin's design also directly serves its namesake's legacy, the search for dark matter and dark energy, the invisible components that, according to current cosmological models, make up the overwhelming majority of the universe's total content. By precisely photographing billions of galaxies repeatedly over a full decade, Rubin will map extremely subtle patterns of gravitational lensing, the way massive foreground objects bend and distort the light of galaxies behind them, across enormous volumes of the observable universe. That data will allow cosmologists to map the distribution of dark matter with a level of precision and coverage no previous survey has achieved, while simultaneously tracking how the universe's expansion rate has evolved over cosmic time, directly informing the ongoing scientific debates around dark energy and potentially the Hubble tension covered in an earlier episode of this series. It's a genuinely unusual scientific instrument in that sense, built to simultaneously advance solar system science, stellar astrophysics, transient event detection, and fundamental cosmology, all from the same continuous stream of data, rather than being optimized narrowly for any single one of those goals. It's worth understanding the sheer scale of data Rubin generates because it represents its own kind of engineering achievement, separate from the science itself. Each full-sky image captured by Rubin's camera is enormous, and across a single night of operation, the observatory generates roughly 20 terabytes of raw data, an amount that would have been considered an extraordinary annual output for many previous observatories, now produced before sunrise on a single working night. Over its full 10-year survey, Rubin is projected to generate an archive measured in hundreds of petabytes, requiring purpose-built data processing infrastructure capable of comparing each new image against previous observations essentially in real time. That processing pipeline is what actually makes Rubin's discovery rate possible. Raw images alone, however detailed, don't automatically become asteroid discoveries or supernova detections. The system has to automatically identify what changed, flag it, and in many cases alert the global astronomical community within minutes, so that other telescopes can follow up on time-sensitive events before they fade or move out of view. Rubin's full 10-year survey has only just begun, transitioning from its commissioning and testing phase into its main scientific operations in the months following its June 2025 First Look event. Nearly everything covered so far in this episode came from a small fraction of the observatory's eventual output: test data, preliminary commissioning runs, and early proof-of-concept observations, rather than the fully operational survey itself. That framing matters enormously for what comes next. If 10 hours of preliminary test data produced over 2,000 new asteroid discoveries and the fastest-spinning large asteroid ever recorded, the scale of discovery expected once Rubin is running its full survey, night after night, for a full decade, is difficult to overstate using any previous astronomical survey as a comparison point. Astronomers involved with the project have been consistently careful in public statements to frame Rubin's early results as a preview rather than a finished accomplishment. A demonstration that the instrument works exactly as designed, with the actual scientific harvest still almost entirely ahead of it. On June 23, 2025, a telescope in the Chilean mountains turned on, pointed its camera at the sky, and in 10 hours of testing found more previously unknown objects in our own solar system than most dedicated survey telescopes find in years. The Vera Rubin Observatory isn't built to look at one thing closely. It's built to watch nearly everything at once, continuously for the next 10 years, cataloging every asteroid, every supernova, every interstellar visitor, and every subtle shift in the distribution of dark matter across the observable universe, all from the same unbroken stream of data. We are, right now, in the earliest days of what may become the most productive astronomical survey in history, and the fastest spinning asteroid, the record-breaking first-night asteroid count, and the millions of newly cataloged galaxies are only the preview. The real 10-year survey is only just getting started. What do you think Rubin will find first? A dangerous asteroid, a new interstellar visitor, or something nobody's predicted? Leave your guess in the comments. And subscribe, because the next classified file goes up in a week.